Just a moment. Actually, it is not allowing to share the screen. I will just log out and log in again.
Okay, one moment. Maybe I'll make you co-host. Maybe that's one moment. Okay. Yeah, just you can try again. I
Just
made
a
you the
moment.
co-host.
It looks like it is not. I'll just join again. So I think that will be okay. Or is it visible
Yeah,
now?
it's visible now. Yeah, it's
It's
visible.
visible, right?
Yeah.
Yeah, okay, fine. Okay, so very good afternoon to all. I think it's I feel really good to present a lecture in this series, and Ramanan sir is also here. So I think it's a very good opportunity for me to show also what I have been doing for the past 6 years since joining VSSC. So I'll start. I think the time was roughly around 40 minutes, but I may slightly overshoot by maybe 10 minutes or so, 10 to 15 minutes. Okay, so I will start. So what I'll be talking about is developing of a CFD solver for aerospace applications. So this is work which I have been doing for the past 6 years almost, not continuously, but on and off. And recently I have been working on it for a long time. This is presently, we are trying to develop an unstructured grid solver in VSSC. And regarding its development, I will show some of the things that we have done and what I have learned basically. I did not have any CFD course as such or a formal CFD course. So all these things I have learned as I was doing. So probably most of the things are from experience. So it may not follow the actual theory of CFD, but I think it will be good. Like in a way, you will be able to see how you can understand the working of the solver and also what all things go into the solver. I will be focusing only on aerospace applications because you know that CFD is used in many other areas as well, like starting from automobile, even in civil engineering. So I will not touch upon any of that because it's a very short duration to explain most of the things. So I will focus on the only things which I found to be useful or which actually make a difference in the solver. And this also I will be talking only one type of solver. There are n number of solvers available or different uh, types of solvers are available. I'll be talking only about one type of solver, that is a finite volume solver. Okay, so I'll start from the applications first. As you know that in aerospace industry, there are also many applications, including aircrafts as well as launch vehicle and re-entry vehicles. So here I'm just showing two of the applications that are used in ISRO or VSSC or in space industry in general. They are launch vehicles and re-entry bodies. In this also, we can make certain types of what you say classification. In launch vehicles, we need certain areas in which CFD is required. That is overall aerodynamics or aeroacoustics. In overall aerodynamics, we use the overall aerodynamic coefficients or forces and moments, which are used in control design as well as trajectory design. Now this overall aerodynamics also, we can go a little deeper and say we need sectional loads or the sectional pressures acting on the vehicle which go into structural design. So this forms a core application for launch vehicle. When we go to re-entry vehicles, overall aerodynamics is definitely important and that also we use, but there is another important application, that is estimation of heat flux. So that governs the thermal protection system of the re-entry vehicle during re-entry. And this has a perfect gas component as well as a chemically reacting component. That means when the vehicle is re-entering into the atmosphere, the air will dissociate in front of it and N2 and O2 will become NO and it will give electrons also. So all such types of chemistry also we need to incorporate in CFD, and that is the air chemistry simulation. This will definitely change the heat flux and also it will have certain impact on the design. Another aspect is dynamic stability. That is, through unsteady simulations, we will need to find out if the vehicle is stable or unstable. So these are some of the applications that I have shown in this slide, for which we use our CFD solver. So I think most of you will know like what is a CFD. I just put this slide there to just recap. We are trying to solve the fluid dynamics equations numerically, and numerically means on a computer. So earlier fluid dynamics equations we used to approximate and get analytical solution and then find out how the flow is behaving. But with now with computers, we would like to solve them on a computer to get a better fidelity. So now when we come to computers, we cannot solve PDEs directly. So we need to convert these PDEs into algebraic equations. And these algebraic equations, we can iterate and get the solution to PDE. So basically now the natural questions will come, how accurate is the solution, or how to convert the PDEs to algebraic solutions, and then how to get the iterative scheme, whether that iterative scheme will converge or not, and whatever solution we get, whether it is actually the true solution or not. So these are many questions which come to mind. And you see that there are many solvers in CFD solvers which try to solve these equations. I have listed some of them. That is Paras, that is in-house solver of VSSC. Then there are commercial also, ANSYS Fluent, CFD++. There is one -3D also, I forgot to mention it here. And in open source, there are SU2, OpenFOAM. If some of you who have used these solvers, they will know that all these solvers behave very differently. Like some of them for a same mesh or a same grid, some solvers will converge whereas some will diverge. And it is very difficult to find out why. So I think probably after this presentation, you will come to know what are all the components going into the solver where this difference can be seen, or which will actually make the difference between the solver converging and diverging. So that is some of the things that I will try to explain. So before going to the solver, first we need to see which equations are being solved. So these are three very simple equations if you look at it from the outside point of view. That is conservation of mass, linear momentum, and energy. I think Reynolds transport theorem will be familiar to all of you. So these are based on that, and the control volume framework, I think these are used. So in a control volume, whatever flux is going in or whatever mass is coming in and going out, the difference of that will reflect as change in mass inside the control volume. And similarly for the momentum as well as energy. This forms basis of all the finite volume solvers, CFD solvers. So what we are talking about today is a finite volume CFD solver. So these integral equations form the basis of that. Now, if you see the equation, there are, we can consider some 3 or 4 different terms. I will come to that classification of different terms. But in general, we have to see that there is a time derivative involved, then there are surface integrals involved, and there is a volume integral involved. So these things have to be discretized separately. And also when we are coding, there are another things also like trivial things of computation of volume, surface area, and surface normal. These also need to be kept into mind, like how to compute that. Anyway, these are trivial things, but apart from theory, when you go to actual implementation, these things also will matter that you have to consider. Then the viscous flux computation that is used in our momentum conservation equation, it consists of basically velocity gradients. It's stress terms, so velocity gradients are also required. So these gradients also play an important role. So this is just to give an idea of what all terms are involved in the governing equations. All these governing equations we can form in a compact form like this, in a matrix form, where W is the set of conserved variables. These are unknowns basically, which we are solving for. And then whatever other terms were there, those we are grouping into different terms. So FC is the convective flux term. Then FV is the FV is the viscous flux, and Q are the source terms. So if we see here, the convective flux or the inviscid flux, what is written, that has a simple form, that is basically the variable multiplied by velocity. And for momentum, pressure is added. Whereas for viscous flux, we have all the shear stress components and normals. And the shear stress components will have velocity gradients included in them. So when we form it into the compact form, it becomes very easier to see how we would like to discretize and which terms we would like to compute. So this is basically kind of partitioning the equations into different modules, which we will be able to discretize and solve separately. So I will go one by one. Like first we'll go like how to calculate the convective flux, then how to compute viscous flux, and so on. Then we will go to the time update or the partial derivative in time. Now, when we saw earlier, now we need to convert these PDEs into algebraic equations. Now, converting PDEs into algebraic equations means that we are not solving the continuous functional solution of the equation, but we are trying to find a solution at some discrete points. Now, this PDEs depend on space as well as time. So, we are trying to find solution at discrete points in space and time. So, first we will see discretization in space. Now, you imagine a big volume around a body around which we want to solve these equations that can be discretized into small chunks of volume. Now there are many ways in which we can do it. So I am showing three of the most common ways. I think these three are used in many of the solvers. So first one is the easiest one, that is the Cartesian grid, in which you just cut the volume space along x, y, and z directions. So you get almost like cubes, small cubes in the entire volume. The only disadvantage with this is that the body will not exactly conform with boundaries of the small volumes as it is shown in the first figure, but still it is used, and solvers exist which use this mesh and get the solution. Another is structured grid, where you are making a rectangular or in 3D hexahedral cells around a body. They are like wrapped around the body and they have a definite structure. And if you know a cell or its ij or its address, you can very easily get your neighbor's values or your neighbor cell's addresses. So because it has a very well defined structure, it's a structured grid. And the third part is the unstructured grid. This unstructured grid is like you are trying to fill the volume with whatever cells you can, that is hexahedrons, prism, pyramids. You just need to fill the volume. So this is very easier to generate, but the solution procedure or the solver for this becomes slightly complicated in order to handle such cells, and as well as some stability issues will come. Also, one point I have mentioned here, that cell numbering. This you can just keep in mind, the cells here, whatever numbers are shown, they are not like one's neighbor is 2. Here one's neighbor is 56 is shown. So this will actually play some role later. So I think you can just keep this in mind, how the cell numbering is random in unstructured grids. So unstructured grid or structured grid, there is a debate. We can use any of them, but unstructured grids are very easy to generate for complex geometries. So usually we go with unstructured grids. So this solver is also aimed at solving PDEs on the unstructured grids. Now we will go to how to solve these equations on this unstructured grid. On the right hand side, I am showing a hexahedron, but it can actually be any other cell. It is easier to visualize in hexahedron. That's why I have put hexahedron. Here we are solving equations to get solution at cell centroid. So it is like averaging the entire solution in that volume to the cell centroid solution. And then whatever surface integrals we had earlier, those are converted into summations or summation over faces. So each face centroid will have its value, and we'll compute flux at each cell centroid and sum it over to get the surface integral contribution. So whatever equation we had earlier, the integral equation, that is now converted to this summation equation with time derivative. That time derivative term is still retained, that will discretize later. So this form is called a semi-discrete form because time is still in partial format, but other equations we have, other integrals we have converted into summations. It is compactly written as dw dt into omega is equal to minus r. This minus r is the residual, which is actually summation of fc, fv, and q. This q source terms are usually zero in this Euler type of equations, or even ns equations, but there are other, when we go later we'll see from where that q term will come. So now here what we need to remember is we are computing solution at the cell centroid, and all our fluxes are computed at the face centroids. Now how to compute the flux? So first term in our equation was fc. That fc had this variable multiplied by velocity term and plus addition of pressure. Now we need to get value of this fc at the face centroid, but we don't have values available at face centroid. We are solving only at cell centroids. So our values of variables are available at cell centroids. Then how to get values at face centroids? Now the easiest thing that we think of is, okay, you just take the average. So you have left side cell centroid value, you have right side cell centroid value. You just take the average and get the value at the face, and then compute the fc. Okay, that is also possible. Another way is you compute the flux fc directly with the left values, fc directly with the right values, and take average of the fc's. So this is another way. Both of these are valid. Both of these actually are not equivalent in most of the cases that you can see later. So here, this is the easiest way, but this leads to some stability issues. And for that, I think initially this was done, but it did not work well. And it was found to work well when you add something called as dissipation. So this forms first set of schemes. So basically these are called schemes in which you are computing FC by some means. So first set of schemes are central scheme with artificial dissipation, which have this structure that FC is average of left side flux, right side flux, plus some addition term. So this is a very simple structure. But the computation of D, or how to compute the D and add it so that it is stable and it gives you the intended result, that is still another topic. Then after that, a few other set of schemes came. So these are called as flux vector splitting schemes. In this, actually, the wave propagation equations or wave propagation phenomena of Euler equations is made use of. So if you imagine, like in our normal case also, we imagine a pressure wave is traveling. So similarly for Euler equations, there are three types of waves which travel in left side or right side. Depending on which wave is traveling on left side or right side, we consider appropriate cells. So now if the flux wave structure, we dissociate in such a way that all the right running waves, whatever flux is associated with right running waves, we put it in FC plus, and whatever flux is associated with the left running waves, we put in FC minus. Now this FC plus and FC minus, we evaluate with respective cell centroid values. So FC plus, which is the along the right running waves, will be calculated with the left cell centroid value, and FC minus will be calculated with the right cell centroid values. So this gives another type of scheme. So these are called flux vector splitting schemes. And there is one concept called upwinding. So you consider the values in the direction of wave propagation or the flow. If simply we see if the flow is going from left to right, instead of considering the right cell value in flux computation, you consider the left cell value. That is called as simple upwinding. That upwinding brings stability to the scheme. So in this case, that upwinding is inbuilt. So with which we need not add the additional term like we added earlier, that D dissipation. So there are various examples of these schemes such as Van Leer, or there is AUSM full family of schemes. There is AUSM, AUSM plus UP, AUSM plus UP2. There are so many schemes available. These schemes work in most of the cases, and they can also be written in the earlier form, central scheme plus artificial dissipation. But each of these schemes, they have different applicabilities. So some schemes work for low Mach number flows, some scheme work for high Mach number flows. So those also we need to consider. Here I am just showing as an example this scheme. We need not go in detail of what all terms are included. This is a AUSM scheme, advection upstream splitting method. In this, there is one more addition, that the FC is written as FC convective plus FC pressure. So whatever rho V terms were there, they are in FCC, and whatever pressure terms were there, they are in FCP. And then again, we are using the ML plus and MRL, that is the left cell contribution and right cell contribution, and we are adding them together to get the flux. Now, I'm just showing this to show like now this involves more complexity than the earlier one. So earlier one was only that you take average of left flux, right flux, and add dissipation. Whereas because now we are going into some physics of the Euler equations, we are going to slightly complex schemes, but these schemes perform better. So that's why these are also used. Now we go to another type of scheme. So there are still some shortcomings with the earlier ones. So we go to the next one. So these are different types of schemes where again that wave structure is used, but here a concept of Riemann problem is used. It is like you imagine a shock tube in which, or even these two cells in which that red colored face is considered as a diaphragm. So left side will have say a high pressure and the right side has a low pressure, and the diaphragm bursts. When the diaphragm bursts, a shock wave will travel to the right hand side, one expansion wave will travel to the left hand side, one contact discontinuity will travel. So all these wave structures are considered in arriving at a flux computation, which is schematically shown on the top side, that rho L UL is on the left hand side, rho R U R on the right hand side. And when the waves travel, that in between at the interface, the values will change. And there exists a solution, exact solution for this problem. So if we are given a left state, right state, then we can actually find out what will be the state at a time after some time, that the star states, whatever rho star L, V L, W L, like that it is written. But actually that solution is an iterative solution which we need to solve. If we start doing it for all the faces, now you remember that now whatever we are looking at is only one face. That our entire volume is divided into so many cells, maybe millions of cells, and on those all millions of faces we need to do this computation. So if we try to find the exact solution for this and compute fluxes, that will be a very, I mean, it may take years probably. So the easier way is you approximate this, and that approximate wave solution you use to compute the starch states and then get the flux. So this also has a separate schemes which are called row scheme or HLLC scheme. These are more popular. They also work in most of the cases, and they also can be written in the earlier form, that is FL plus FR by 2 plus some artificial dissipation term. Here I am showing the one of the popular, that is row scheme. Here also I am showing not the actual scheme. It is basically I just want to convey that how it is written. So if you see on the left bottom that FC half, that is at the face, is written at FC plus FCL plus FCR by 2 and some D. So this is A rho into WR minus WL. And again that value A rho into WR minus WL is shown on the right hand side. That is delta F1 plus delta F234 and delta F5. So you can see now we are going from the easiest one to the complicated one. So here this actually is the D. So whatever we could have added earlier manually, whereas here it is automatically coming from the scheme. And these schemes have certain properties, and because of that they are chosen. So row scheme usually we use for low speed flows or even up to say Mach number 1.2, 1.4. But for a higher Mach number flows, this scheme is known to give some phenomenon which is not actually physical in stagnation region. So then we need to choose another scheme. Now you can understand why so many schemes are there. There is no unique solution for this. So there are another entire types of schemes which I am not covering here. But now you can get idea how that solvers are being different. Each solver will use its own scheme. So that will lead to how the solver behaves. Now, when we consider all these schemes, there are certain types of conditions it needs to satisfy. First one is the consistency. That is, the errors should go to zero when you refine your grid as well as you refine your time step. So all these schemes will follow this, and it is an important property. If it is not satisfied, then the solution will be totally different. We are not actually solving the PDEs. Then next question is that how accurate is the solution? So all these schemes will compute flux, and when we compute flux and update, and we will get a solution. So that order of accuracy is also very important. So if the error is proportional to the cell size, it is the first order accurate. If it is proportional to the delta x square, then it will be second order accurate. Now, how to improve the accuracy of the scheme? That also can be done by changing the or considering variation inside the cell. Now, what we saw earlier is we are considering only the cell center value, and that cell center value is put everywhere in the cell. Whereas if we consider a variation within cell, like a linear variation of variable, then that can give us a higher order accuracy. Also, there is another type of accuracy. We are now considering flux integration only at single point. We are computing flux at face centroid only. But this also, if we compute at multiple points, like a quadrature, say 2 points, 3 points, 4 points, then again that integral accuracy will increase. So this gives to rise to another types of methods like higher order methods and all. So that I will not go into. I think I have covered up till now. So if you have any questions till now, then I think this will be right time to pause for some time. Then we'll go into evaluation of next term. So if anybody has any question, I will just pause for a couple of minutes. I think Padmanabha wants to ask.
I have a question. Do you know of any commercial codes that actually make use of artificial dissipation type of methods?
It is like what I know is in commercial codes, they will use one of the schemes, but they will also add some additional dissipation. It is like along like even in CFD++, if you see there is one tuning coefficient, like you can add or tune the dissipation. This is over and above this scheme. So it is kind of artificial dissipation only, not in the exactly the same form, but it will add certain amount of additional dissipation over and above the scheme.
Okay, so you mean to say that most commercial codes are overly dissipative, and even if you select second order spatial accuracy, you may be only as good as a first order scheme.
It may not be exactly first order, it will be mostly second order only. But yeah, it is possible to get a first order if you add a lot of dissipation. That dissipation control is given. So if you add a lot of dissipation, it will be as good as first order only. Yes, that can happen.
Okay, thank you.
Okay, so actually what he was asking, I will just show here also. This is a reconstruction. This is how we get a second order accuracy. Here earlier what we did was we had a value at the cell centroid on the left side and value of cell centroid on the right side, and we used it for computation of fluxes. So instead of that, now we say we will consider variation within the cell. So here we are considering linear variation in which we compute the gradient, and using gradient we reconstruct to the phase. So it is like solving, it is like getting y equal to mx plus c. C we already have, that is the cell centroid value. Where if we compute m, then we can get the variation y is equal to mx plus c for any point in the cell. Now that m or the slope computation is another way, so that I will come to later. Now once we know the slope, so assume that we know the gradient, then we can use this equation to get value at the face from the left side, and similarly a value at the face from the right side. That value will be different than the cell centroid value. Then instead of cell centroid values, we will use these values to compute the fluxes. This will give us additional or second order accurate solution. But there are certain things which we need to see here. This can lead to divergence also. If that UL, whatever is shown in figure, which is the reconstructed value, it can be higher than the neighboring cell value, because if the gradient at I is very high, then that UL can definitely be higher than the next cell value. So you can imagine that it will form kind of a peak or a maximum at the face, which is higher than UI and UJ. This can induce some type of oscillations in the solution, and which can grow and cause divergence. So for this, a limit.
Hello, I think your voice got broken. Aditya. Hello. Hello. Hello.
Sorry, I think my internet got disconnected. Am I audible?
Yeah, bhai, you are audible, sir.
Yeah. Okay, can you see the screen?
Yeah, yeah, okay.
Yeah. Okay, so okay, I'm not sure where I got disconnected. So I was at this slide, right?
Yeah.
Where we're about computation of gradients.
Yeah, yeah.
Okay, so now we'll look at computation of gradients, which are required for getting the second order accurate solution or reconstruction. For that, now we remember that we only have values available at our cell centroids. So based on the cell centroid values only, we need to construct a way in which we will get gradients. The first thing that is used is the Green's theorem or Green-Gauss theorem, in which the volume integral of a gradient is equal to surface integral of values, which is shown here. So gradient at the cell centroid or UI is summation of that U over all the faces. This principle is used in computing gradients. Now here we can see that we need value at the face, which is not directly available, UF. We only know UI and UJ, but we don't know UF. So how to get this UF? Again, there are n number of possibilities for this. First, easiest is you take average of UI and UJ. So that is shown as the first one. Or second one is you compute values at N1 and N2, which are shown as nodes. So to get values in N1 and N2, again, you need to take averages of I, J and any other neighboring cells for which N1 and N2 are common. And then take average of UN1 and UN2. So now you can see that there are multiple ways in which we can actually get this UF. And some of these ways can give a better result than the other. That will depend on your grid topology and all such things. So that's why now for gradient calculation also, we are going into multiple ways. There is another way, that is the third one, which is shown as diamond path. This is also used in solvers, in which actually we are not getting the gradient at cell centroid, but we are getting it directly at the face. This may seem slightly odd because now what we have seen is that for gradient computation, we need gradient at cell centroid, but we are computing at the face, but actually for the face is required later, which I will come to. In this case, what we are doing is we are considering a fictitious cell about the face, and then again getting value at the face centroids of the fictitious cell, and then using this Green-Gauss method to get the gradient. If we don't want to use Green-Gauss, then there is another way called least square gradient. You can imagine if we write it as a Taylor series of Uj with respect to Ui, and then we can get equation like this, where the difference between Uj and Ui can be written as a gradient times the distance vector between the two. Now in this figure, there are actually only 3 neighbors, but in 3D, they can be 6 neighbors also. So if we have 6 neighbors, then this equation will become a matrix equation in which the unknowns are the dou x, dou u by dou x, dou u by dou y, dou u by dou z, and the matrix or the system will be overdetermined, in which we need to solve for these 3 unknowns, but we have 5 or 6 equations. So that's why it is solved in least square sense. And then if we solve this equation, then we will get approximation to these gradients, which can be used. Here also sometimes the weights are important, like some cells are weighted more as compared to other. So there are different types of weights, like you use 1 over distance or 1 over distance square, and those weights also can sometimes make a difference. They may not be much, but they can make a difference in your solution strategy. I think Padmanabha wants to ask something.
Aditya, since you mentioned up to second order schemes in your convective flux part,
Yeah.
is there any benefit to going above linear? I can see that the matrix equation written here is for a linear least square fit.
Yeah.
Is there any benefit to going to higher order for estimating viscous fluxes for your gradient estimation?
I think you can go to second order accuracy, but it is not always possible. Like you can estimate your gradients in second order way. It is usually desirable, but it is not usually done. We'll go with first order only or linear fit only, because I think that has some stability issues when we put it that way.
Okay, thank you.
Or otherwise, that quadratic also you want to ask, like whether we are doing only linear reconstruction or quadratic. Is that what also you are asking?
Right.
Okay, that also what you're saying. In that case, actually, if you want to go for a higher order, then we need to have another like more points on the face also for flux quadrature.
Correct. But I think for up to second order, you can use 1 point only, no?
Yeah, up to second order. So with linear reconstruction, we'll get second order accuracy. So that's why for second order, linear is sufficient.
Okay.
Okay, so now once we have gradients, we can actually compute viscous fluxes also. So the gradients we use for reconstruction as well as for viscous fluxes. Now when we come here again, we have that dilemma how to get gradient at the face, because again when we come to flux, we need at face, whereas for earlier reconstruction we needed gradients at the cell centroid. So easiest way again is to take average of the two. You take gradient of left cell, gradient of right cell, and take average. But this is known to lead to odd even decoupling, or the solution in even cells are not related to solution in odd cells. So that can give you oscillatory solutions. So that's why you need to add another additional term in that, which is shown here. It is like whatever directional derivative you have from left cell to right cell, that component you remove and substitute it with another uj minus ui by l term. I think there are not many variations in this. There are only a couple of things that I know, like this additional term is slightly different in other variations. But most of the times viscous fluxes are discretized like this. Now, earlier I had told that in diamond path, we are getting viscous or the gradient directly at the face. I think this is the reason for that. So in diamond path gradient calculation, that gradient whatever we compute there will directly be used in viscous flux computation. So that is an advantage, but the disadvantage is again we need to compute for reconstruction gradient at cell centroid. So again we need to take average there. So it is like, anyway, we have some advantage or some disadvantage, and we have to choose from any of these schemes available. Now that completes the first part of the convective and viscous flux computation. Then we come to time discretization. So we have only dou w by dou t till now. Now right hand side RWN is already computed, that is FC, FV and Q. Now how to compute dW by dt? Now dW by dt we can write it as delta W by delta t, and as you can see on the left hand side, that becomes a very easy explicit scheme, like at that new time step minus present time step is equal to a right hand side which we have already evaluated. So this is the easiest way. It is explicit scheme. It is still used in few solvers, whereas the right hand side is implicit scheme where RWN plus 1 is used. So that is the residual at new time step. So that we need to again use the Taylor series to convert it into whatever things we know, that is RWN. We know the flux computation at the present time step. So when we convert it to RWN, we get additional term of dou R by dou W. That is the gradient of residual with the values. Now you see, if this is a derivative of a vector with respect to a vector. So this gives a matrix, and there are also interdependencies. So if we see the left hand side, that dou R by dou W term, this matrix is actually a size of number of cell times the number of variables. So if we have millions of cells, then this size of this matrix is number of variables times those many millions of cells. So it becomes impossible to solve this, that ax equal to b equation. So we need to go for some matrix free methods, which we'll see after a couple of slides. Now when we come to explicit scheme, as I told earlier, this is a very easy scheme. So you march cell by cell, you go to first cell, you already have computed the fluxes or the residual, then you just multiply it and then get the delta W and add it to your present solution, and you will get the new solution. So this is a very easy marching scheme. Now additional complexity can be added by going for multiple steps. Like you don't update it in a single shot, you go for a smaller time step, then again compute the residual, then again update it, then again go for a smaller time step. So in multiple steps, you reach your final delta t. So this is called as a Runge-Kutta scheme. So this has certain advantages, like it is more stable and can be used for second order time accurate simulations also. But wall clock time wise, what we have seen is either you go for 1 or 2, it doesn't matter much. The simulation time will be similar. The simulation time will be drastically reduced when we use this implicit scheme. But implicit scheme is very difficult or slightly complex to implement. So here I am showing graphically, this is basically like a map of each cell depends on how many other cells. Now if you see at the first figure in center top, the diagonal blocks what are shown are the present cells. Now the present cell we want to update, it has dependency on all its neighbors for flux computation. Now what I had told earlier, in unstructured grid, your neighbor may not be numbered sequentially. So if your cell number is 1, your neighbor is not 2. It may be earlier, I think it was 56. So here if you see, that dependency is whatever is the again non-zero block in the same row. So if you see the dependency matrix, it is very sparse. Like first cell has dependency on it, like say 56, 100, 200, like that. So the matrix structure is sparse, and this we need to solve in actually our x equal to b. In order to get a solution to matrix system, we need to convert this first to almost like a banded matrix. So this is done through a reordering mechanism in which the cell numbers are again reordered. So you go from your cell to neighboring cell, then make it as 2, then its neighbor make it as 3, like that. So this is called as reverse Cuthill-Mackey cell reordering algorithm, through which you can get a kind of a banded matrix. It is still not tridiagonal or pentadiagonal system, but it is very close to that. And this then can be solved by any of our linear solvers, which can solve Ax equal to b. So one of the solvers is symmetric Gauss saddle, in which what we do is we go to the first cell, we find out what is the change, delta W, then we go to the next cell. Now when we are computing delta W for the next cell, we make use of the delta W computed for the first cell. So similarly, we keep on adding this influence of earlier cells in our update of the present cell. So this gives a kind of a feeling that even the last cell in the domain which we are updating has influence of all the other cells which it has already updated. So in this way, this scheme, we intuitively feel that it will be more stable. So now consider explicit versus implicit. Suppose the present cell number 1, that update is found to be say 100. Then the neighboring cell, the update can be 200 because it is actually independently updating with respect to first cell. Whereas in implicit, if first cell update is 100, then second cell already knows that the first cell is updated by 100, and with that effect is taken into account while updating the second cell. So that gives us comes to a stability of the schemes. Now, what I told earlier, that influence of different types of cells are considered in updating the solution, that is in a way related to a CFL condition, which is told as the domain of dependence of numerical scheme should include domain of dependence of PDE. That means if a solution at time delta t, after like t plus delta t of the PDE will depend on certain region around your x point. So in the figure it is shown XL to XR. So solution at t star depends on XL to XR. So whatever numerically you are computing solution at t star, your numerical domain or the number of cells should also include this domain. So your leftmost cell should be before XL and rightmost should be after XR. Only then your scheme will be stable. So this gives that explicit schemes have a limited stability, whereas implicit schemes are theoretically for linear advection equations, they can be stable for even a very like almost infinite CFL number. So that's why this CFL number is important.
Aditya, can I ask
Yeah.
this? So does this CFL criteria hold for equations which are not hyperbolic also?
These are for hyperbolic only.
Okay,
Mainly
so
this is given for hyperbolic only, for wave type of equations only, because then we have real characteristics. So this CFL criteria is mainly for hyperbolic only. As Padmanabh also want to ask.
Yes, Aditya. The thing is, if you're solving Navier-Stokes with viscous effects,
Yeah.
you will have a time step limitation that comes in through the second derivative discretization also.
Yeah.
Is that typically a problem in CFD that you have observed, or is it not an issue? And CFD?
Not really. I have not seen it. Usually only this CFL only will be governing, not the other one.
Okay.
I think that goes as delta x square, right?
Correct. So the time step limitation would be smaller depending on the.
But I have not seen that usually.
Okay.
Usually this condition only will govern. Okay, so now in order to analyze it in a different way, there is another something called von Neumann stability, in which the error after each iteration will be analyzed. So whether that error gets amplified or it dissipates, and different. So for that, you take a Fourier transform and then do the analysis, from which we can find out if error is of particular frequency, whether it will amplify or damp, and that is found to be like it varies with frequencies. This is another type of analysis which can be done for these schemes. And then another type in which nonlinear stability or total variation diminishing monotonicity preservation, these things also come. Because for I think non-linear schemes, the stability analysis is not very sound. Like we cannot actually do the stability analysis for all the schemes. So these are some guidelines, or from this we get some idea, and then we have to do numerical studies only to find out which schemes actually how it behaves. And the thing that we can control in this is CFL number. So if our simulation is diverging, then the only thing we can control is basically CFL number. So if we reduce CFL number, that is basically we are trying to reduce the time step, and time step is reduced. That means we are considering a smaller domain of dependence, and that gives better stability. So from this actually explicit schemes, the CFL roughly is less than 1 or sometimes even less than 0.5 or 0.4. Whereas for implicit with symmetric Gauss saddle, I have tried some simulations even with 1000, 10,000 or 1 lakh CFL. So it is like after a certain point that CFL number does not have any meaning as such, but even for very high CFL, it goes through. Now one point, yeah, Padmanabha wants to ask.
I have another question.
Yeah.
So when you do symmetric Gauss seidel, if you're it's fine if you're looking at steady state solution.
Yeah.
But if you want the unsteady solution, that is time varying solution, are explicit methods better to use for time varying solutions?
Yeah, actually here I'm not talking about time varying at all, because I think that is a totally different thing. The only thing I can say is if you are looking for global time stepping, then it is anyway explicit only. But if you are doing local time stepping in which you have fixed a time step, then whatever internal iterations you are doing, you can still use SGS. So the number of internal iterations required for that convergence will be much smaller for SGS as compared to explicit.
Okay.
So you can still go with SGS implicit if you are using dual time stepping for unsteady simulations.
My question is due to the nature, one cell updates the next cell even before the entire domain has updated.
Yeah.
There is some dependence on the next cell on the previous cell that has been updated. Right.
That is like if you see the dual time stepping equation, then in the dual time stepping equation there is additional term. So we are not actually solving this equation.
Okay.
We know the solution after delta t. Suppose if the order of accuracy in time is second order, from Taylor series we know after delta t the solution should be this, and we are trying to reach that solution through SGS. So it is not exactly this equation. There is additional time dependent term which comes in.
All right.
So that way it is like the internal iterations are like going to a steady state only. So there this will not matter.
Okay.
Aditya, I have a question.
Yes, sir.
Just as a research thing, this dependency on CFL number, is it possible to eliminate that? We can devise a new scheme completely coming out of this. Is it not possible? We don't think on that line.
I cannot give a directly answer because whatever I have seen, usually some dependency. Even if we go to implicit scheme, theoretically it is not dependent on CFL as such, or the Newton iteration. What we see that Newton iteration is not dependent on CFL, but that is for linear equations. It is possible. For non-linear, still that CFL comes into picture. Like we have to go with smaller CFL only. Somehow
that's right. I agree, because the way we have defined the schemes, it makes dependent on CFL number. That is what my opinion is. Okay, but whether any other scheme we can devise a new scheme totally different from this, which is divide of CFL number, something such that the stability is very important. But this argument is very weak. I am seeing very weak argument that stability depends upon CFL number. That is really not a very welcome situation. So think about. I don't have an answer. I am only just questioning.
I would also think actually this is the most critical thing what we face in our CFD simulations.
I know.
We keep on reducing our CFL number till we get strategy.
Exactly.
Solution. I will also think about it.
Please.
Okay, and there is one more point which we have not talked about, but which is very important, is boundary conditions. Actually, this is also not discussed much, because all the schemes we are talking about only faces. We never go till boundary, but boundary conditions can play a crucial role in actually making your solution convergent or divergent. If the boundary conditions are not properly implemented, then the solution will not converge. There are three different types of boundaries: wall symmetry and inflow outflow. Wall symmetry are straightforward, but inflow outflow, again, there are a number of ways in which we can do. So this is one type what I'm showing. These are called Riemann invariant boundary conditions. So again, we make use of the wave structure. So whatever waves are going from left to right or from domain to outside, we make use of the domain values of the variables, and whichever wave is coming from outside to inside, we make use of the free stream values which we have given. But discretization of boundary conditions for implicit schemes is also very important. If the boundary conditions are not implemented in implicit way, then the stability again will have certain issues. Then the CFL number again will be limited. Now we come to another important point. Till now we have talked about NS equations. Now we come to RANS. So we need to include the effect of turbulence. So this is basically chaotic motion of the fluid particles. Then how to include that? One way is you keep on going to a smaller time step as well as smaller space volumes, so that you capture everything. So there is no need to model anything or do anything special. You just solve the equations on a very small volumes at a very small time step. That is called as a direct numerical simulation. But the computational resource required for that is tremendous. Even for if we relax that slightly, then we get large eddy simulations and things like that. But for our regular usage, what we require is very quick simulations. So for that, what we do is we model this. So whatever perturbations are imparted by turbulence, those will be averaged over time. And when we again look at the equation, they introduce two additional terms, one in momentum equation and one in energy equation. That is the Reynolds stress tensor. Now Reynolds stress tensor, this again has to be modeled. Now the most commonly used modeling strategy is the Boussinesq hypothesis, in which we say that this stress tensor is just like our earlier stress tensor, in which we used a viscosity. For this stress tensor, we will use a eddy viscosity. It is like adding additional viscosity to whatever viscosity we had earlier. So all the turbulence is now captured into that mu t, or the turbulent viscosity, and that will augment our viscosity as well as our conductivity. Then we need to find this mu t again. When we need to model that mu t, then again we have additional equations. First one is the very commonly used Pallart-Almaraz model, or SA model. This is the one equation in which we are solving for nu tilde. This is just like eddy viscosity only, but slightly different. So we solve for that in the equation in our regular conservative equations and compute mu t. Or we add two more equations, that is for turbulent kinetic energy and dissipation. This is, I feel it is more physical. Like we see areas in which turbulence is created or turbulence is destroyed, and from that we compute mu t. So these are the most commonly used models. The second one is SST, or shear stress transport model. It is basically derived based on two earlier models, that is K epsilon and K omega models. It's a blend of two, and it is more commonly used. So once we get mu t, then we just need to plug it in our momentum equations and energy equations to get the effect of turbulence. So this actually increases our variable size by one or two, depending on which turbulence model we use. And this also we need to implicitize the source terms, whatever we saw earlier, Q. It was mostly zero in other cases. Here it will be non-zero because turbulence is produced as well as it is dissipated. So here the turbulent source terms will contribute, and those also we need to consider gradients when we are using the implicit scheme. Now we come to another important area, which is parallelization. Now when we are solving these millions of cells, we cannot just solve it on a single core, or basically we cannot just update one cell, then second cell, then third cell like that. Then it will take very long time. So we would like to parallelize. We would like to make use of all the cores that are available in the machine. So the strategy that is used is you divide the entire volume into small chunks of volumes and give each chunk of volume to a processor to solve. So that processor will be in charge of all the cells in that volume. It will compute that convective flux FC, FV, Q, everything, and it will update also. Once it updates, then it will again go to the next iteration. But there are certain things which we need to take care of. So here you can see that certain cells I have marked with crosses. If you see at the red boundaries, these are the, say, consider that first left top is given to processor 1, right top is given to processor 2, like that. Now when we are computing values at the black crosses, you remember that the flux computation depends on that cell as well as neighboring cells. So that cell's neighbor is actually a green cross, which is corresponding to second processor. Now if that value is not available, then we cannot compute the flux in the first processor, that black cell. That is why this communication is important. So what is communicated is the cell values. So after each iteration, each processor will communicate with all other processors, and it will interchange the values of cells which it requires. So here this blue processor and black processor are the cells which are required by other processors for their computations. So after each iteration, this will be done. So this is called a communication step. So this will have certain overhead in computational time, but the benefit that we get in reduction in computation time because of this parallelization is much more. That's why we go for this. Also, one more small thing to consider in this is the implicit scheme. In implicit scheme, we were doing like a marching within that on a particular loop or a particular path. So now that path also will be corresponding to particular processor, and whatever boundary cells fall on that path, In that implicit loop also we will need to communicate the second processor's values in order to update our cell. So this also needs to be kept in mind. So that's why for implicit scheme it is slightly more complex, but it is possible. And with this, the turnaround time of the simulation can be reduced drastically. But that also up to a level in which the communication time then becomes more than your computation time. But that usually is never reached because the number of cells are very high. Now coming in nutshell, this is the flow chart what we saw earlier. This is what the entire solver is. So first left part is only pre-processing. When you read the grid, process it, then partition what we saw earlier, the parallelization. We partition the grid and give it to different processors. Then we read the configuration parameters. So what we need to solve, what are the free stream pressure, temperature, density, velocities, then which scheme to use. All these can be given as the parameters from a file. Then we initialize the solution and then we start iteration. So whatever blue box is given, that is the iteration loop. Now, whatever we saw earlier, this can be combined into only 4 steps. First is computation of gradients. These will be used for reconstruction as well as viscous fluxes. So once we compute gradients, then we reconstruct the variables for second order accuracy. If it is only first order accurate we want, then this step can be avoided. Then we go to computation of fluxes, that is convective and viscous, and then we go to update. So that update can be explicit or implicit, and this we keep on doing till we get a convergence. Now whatever we have done till now, how to check whether that is right or wrong. So that solver validation is another important part in which we need to solve multiple cases for which solutions are available, and then see if our solver performs well or not, or if it is the solution what we got from our solver is matching with the analytical solution or already reported solution or not, or even the experimental solution. Here also there are actually 2 steps. One is verification and validation. That verification is just to check whether whatever we have implemented is right or wrong. There we are not worried about if we are properly replicating the flow physics or not. Whereas for validation, we are looking at if we are properly replicating the flow physics or not, or whatever PDEs we are solving, or our solver is solving, whether that is correct or not. So I'm just here listing few of the cases that are like a standard cases which we do. They solve from 1D to 2D to 3D. So left side is the most basic case. This is what we told earlier, that is the Riemann problem or a shock tube problem, where you have 2 states, left and right state, separated by a diaphragm, and then waves will propagate when the diaphragm bursts. For this, exact solution is available. So this is a very good validation case to check the scheme, whether we have implemented the scheme correctly or not. If your scheme is able to capture all the waves properly, that means the implementation of scheme is correct, which is shown on the left hand side. Then right side is for validation of our viscous flux computation. So this includes our gradients as well as viscous fluxes. So this is another simplest case. This is a boundary layer profile over a flat plate. So we have a Mach number 2.54 or even subsonic cases where there is just a flat plate and there is a flow flowing over it, and we know the boundary layer profiles. That is measured from experiment, and we just try to compare from our solver whatever boundary layer profile we got, how it compares with the solver. These 2 form very basic cases which we need to validate our solver with. Then we go to slightly complex cases. This is again 2D airfoil. For airfoil also there are multiple cases from various Mach number ranges, subsonic to transonic. In that case, we will need to match whatever the pressure distribution on the airfoil as well as shear stress distribution on the airfoil. Also for supersonic cases, we would like to simulate the shock waves. So for shock waves, the easiest way is this wedge or cone. In wedge or cone, we know the solution of wedge or cone, and we will try to match our post-shock to pre-shock conditions, whatever we got from the solver, with analytical solutions. Then we go to 3D. In 3D, that airfoil becomes wing. Then for wing, again, we compute what is the pressure as well as shear stress distribution, and we try to match it. And in coming to our area, this is like a heat shield configuration. In the heat shield for different Mach numbers, again, we can simulate and we know the data or the pressure distribution which we can match. Now, what we have seen is a validation. Actual scenario is actually quite different. So when we go from validation case to actual scenario, the first thing you'll notice is the grids. Here, I'm just showing some sample grids for launch vehicle configuration. You can just see there are a lot of protrusions, lot of small things, and the grid structure is quite complex. You can also see if you have done any grid generation that there are prism layers. These prism layers, when they collide, the cells are not very good. So what we have done earlier, all the things will work well if we have all hexahedral grids or all regular tetrahedrons, all good cells. But when we do this actual grid generation, we are bound to get some bad cells or cells which are very skewed, which have very small volumes, very small face areas. Sometimes we have even seen cells which have partial negative volumes. This is another example in which there are also a lot of protrusions, nodules, antennas, fringes. So you can just, this is, I am just putting this in to give some flavor of what type of grids we generally use in our simulation, and the solver should cater to these grids. So it is not always possible to even get prism layers everywhere. So even with this, we will need to handle it, because it is not always possible to create excellent grids in all cases, because the time required and effort required for that is tremendous. And even if we get a very good grid, the number of cells may be too high. So in order to balance that, we have to make use of whatever grids we get. So catering to this requirement is an important aspect. And even with the grids, we would like to get solutions like this. So for that, one key piece in this puzzle is the solution moderation. So these are all other pieces what we have seen already in gradient calculation, turbulence modeling, convective flux schemes, implicit time marching. But solution moderation is actually a key piece which is required for industrial level CFD solver to handle all these grids. So what is the solution moderation? It is basically in we are now going to ad hoc some strategies. It is not theoretically shown or proven, but this is based on experience only. So solution can diverge if the grid is not very good. So cells are skewed, orthogonality is poor, or some negative volume cells, or either sometimes the solution update becomes too high or too low. Such as which we have seen in hypersonic cases. If there is an expansion region, then the solution or pressure will suddenly go negative. So in such cases, we need to have some strategy in order to handle this solution. So there are certain fixes or some strategies which are widely available. One is the local time step reduction. This is again the CFL number. So locally we reduce the CFL or delta T, so in order to control the scheme or to stabilize the scheme. Another way is you reduce the solution accuracy to first order. So we don't reconstruct, so there is no point of oscillations being created, and so our scheme will be stable. Even this doesn't, sometimes it won't work. So in that case also we'll get some unrealistic values such as negative internal energy or negative pressure. In that case, we need to substitute with realistic values. So these realistic values can be anything. So that depends on, it can be tried and tested. There is no unique solution to this. And also turbulence can sometimes create problems, because the rho k or rho omega values, they can become very high, and then the mu t becomes very high. So this in turn, when it goes to our momentum equation, that can also hamper the stability of the scheme. So these variables also can be controlled in some way. So when we do all these things, again, this is like we are trying to build robustness in which we are reducing accuracy. But in order to run the simulations, multiple simulations, and get the solution, then I think somehow we need to balance. So how much robustness we want against how much accuracy we want. So that will depend from person to person or from the requirement. But this is a very difficult task, and this I think only comes after we do a lot of simulations and we gain a lot of experience. So we are actually in the process of doing this right now in order to get results from the simulations. So I think that is what we have done till now, and this is what I am planning to do in future. So this has two parts. One is building capability as well as reducing the turnaround time of our simulation. In terms of building capability, one thing which I have not talked about is the multi-species simulation. So what we have talked about is only air or some single species which we are simulating. But in most of the cases, when we want to simulate our launch vehicles with jets, so these are like two species, or even re-entry bodies, whatever I talked about earlier, air chemistry, there are multiple species, or even combustion. So these capabilities we need to add. So most of the solver structure, whatever we saw earlier, that works for these cases also with some additional equations. Even the schemes work for this, because these equations also will have convective and viscous and source terms. So same structure basically. So this is an extension of the earlier solver. And in order to reduce the turnaround time, what we saw that implicit scheme gives better performance as compared to explicit scheme. Still, there is a better thing called multigrid, in which there are different levels of meshes from finest to coarsest, and we sequentially solve the simulation on these meshes. So first we start with coarse mesh. We will get a solution. We map it to the finer mesh. We get a solution. We map it again to the finer mesh. We get a solution. In this way, if we do, then the errors damp out very quickly, and the solution turnaround time is reduced. But still, here we need different structures of grids and things like that. So this is another involved development. But we are planning to do these things in near future. I think that's all. So I would like to acknowledge many people. So from our BSSC, Harichand MB and Dr. Ashok, they were the initial developers of the solver. And Harichand MB is also responsible for this parallelization, pre-processing, post-processing, all these things he has done. And even the initial solver he has written, from which I have taken over. Also, all our members in our group and CFD division, now we are in a phase where we need to do a lot of simulations. And when we do a lot of simulations, we'll go into different problems. And from those problems only, we will try to find out solutions of which is not working or which needs to be improved. So they have really done a lot of simulations now, which gives insight into where we need to improve. Also, all our heads and as well as group director, they constantly keep on supporting. When I think Pankaj sir is here, he will also agree. He has also supported a lot. And DDRO, he actually started the activity. Our Dr. V. Ashok, he is now DDRO, and he keeps on reviewing it regularly, as well as giving some guidance to which direction we should go and how we should go about it. And recently a team was formed for development of this solver by Director VSSC, and he has also reviewed it regularly, and he also has given guidance. So I would like to acknowledge all of these people. Without them, we would not have reached to this level. And these are the references which I have followed. So many of the equations also I have taken from the first reference or some of second. I think first one, that is by Blazek, Computational Fluid Dynamics Principles Application. This is a very good starting point if you want to develop a solver. And then if from there, it is like whatever I have given overview, a similar overview is given with more details. But if you want to go in depth of say numerical schemes for convective fluxes or time discretization, then we need to go to the next two references, that is by Toro and Lani. Toro is actually a book only with flux computation schemes. So it has all the rho, HLLC, AUSM and all such things. And it has given background for how the scheme is developed, how it is used and all such things. Lani is a general book, which is I found it better for the stability, accuracy, and consistency, all this type of analysis and other analysis. The fourth reference is for viscous discretization only. So this is a PhD thesis by Dr. Muni Krishna. He is also a developer for Hyphen 3D commercial CFD solver. So this is IISC's PhD thesis. He has actually analyzed many of the viscous discretization schemes. And he has come out with which scheme is better or which scheme has a better robustness or better stability. And for turbulence modeling is the last reference, that is by Wilcox. He was original proposer of K omega turbulence model, based on which again this SST model also has come. So that is turbulence modeling for CFD. This is the last reference. So if you are interested, you can go through this. There are many more papers, like infinite papers we can see. But I think these five are the good starting points if you want to go here. Okay, that's all from my side. Thank you.
Yeah, so if somebody has questions, we can.
I have a question on. So when you were mentioning multi-grid schemes, you were interpolating the solution from H to 2H, or that from one cycle to the next. So are there any people who consider some sort of Richardson extrapolation based schemes for simultaneously getting a higher order estimate of the solution?
I have not seen. I'll have to see that. What are multigrid now? Whatever we have seen, it's either three types we have seen. One is algebraic or geometric, or even there is some new type called mode multigrid. But I have not seen for a higher order.
Okay.
It is like basically we are solving the same equations with same order of accuracy, or sometimes only Euler equations also. It's not like entire fully NS also. That also I have seen. Like few people solve only Euler equations on coarse meshes, and only on the fine mesh they solve pure RANs. But
Okay.
that is all second order only, or even first order, but not higher order.
Okay.
I feel that effort required may be much more, and it may not be that much beneficial probably.
Yeah, I have another question.
Yeah.
So since you mentioned combustion simulations,
Yeah.
but typically that will have multiple time scales. You have one time scale for your flow,
Yeah.
whereas your chemical reactions will occur at a much faster time scale. So your equation system will become very stiff.
Yes.
So is it that you only go ahead with implicit schemes for that situation?
Yeah, we usually go ahead with implicit only, but there are certain additional under relaxation involved in that. So for say these additional equations for species, you can have additional under relaxations, but implicit scheme usually is sufficient.
Okay. Are there, let's say you also want to do a time accurate simulation,
Hmm.
hypothetically speaking, is
Hmm.
it possible to do implicit stepping only for the uh, chemical components so that you can achieve the same time step size as your fluid flow equations?
Yeah, I have not done that, but I think it should be possible.
Okay.
Because what I told earlier for dual time stepping, in dual time stepping also we are doing same thing. We are using implicit scheme only in order to go fast. So I think here also it will be possible. If whatever you're talking unsteady simulation with global time stepping, then
Yeah.
it won't be possible. Because there you are, when you are marching with explicit scheme, then that time step is governed by whatever minimum time step is there.
Yeah.
Dual time stepping, I think it will be possible with implicit. I think even commercial solvers like CFD++ and Fluent, they use this like dual time stepping, and for inner iterations, it will be implicit scheme only. So it will go very fast.
Okay. Thank you.
Yeah, so do we have any more questions?
No question. I have a comment. I want to compliment Aditya for
Yes, sir.
taking this type of effort. So
Oh,
I
thank you,
wish you
sir.
all success. You finally know we must avoid all commercial or non-commercial free softwares. All that you must reach that type of status. Okay. I wish you all success.
Yeah, we are aiming for that.
Yeah.
So hopefully we'll reach that level soon.
Yeah. Good. Good effort. Yes.
Yeah, thank you.
Yeah, so if there are no further questions, we can all thank Aditya for this talk.
Yeah,
So
thank
that
you,
we
sir.
can conclude the session now. Okay, thank you all for attending the. So somebody. Okay, so we'll conclude the meeting now. Thank you.
Thank you.